Hi, thanks for joining me today. I've got a really interesting infinite series problem. We want to know whether or not this infinite series here converges or diverges. So it's the sum over all primes p of 1 over p times log of p, where here log of p is the log base e, so the natural logarithm. Now, why is this interesting? Because we know a lot about two very similar infinite series. We know that the sum of 1 over n log n, where n is just over all the natural numbers. This thing here, or I should say n at least 2, so I don't divide by 0. This thing here diverges. And we also know that the sum over the primes p of just 1 over p, this thing here also diverges. But does it change when we add this extra factor of log p on the denominator? Okay, so if you want to investigate this infinite series and see if you can work out whether this converges or diverges, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so it turns out that this infinite series here converges, i.e. will be less than infinity. Of course, we have to prove it, and before we dive into a proof, I'll mention that there are in fact a few different ways you can prove this result, one of which is using the prime number theorem. And if you use the prime number theorem, you can prove this result in just a few lines of argument. But of course, the reason I'm not using the prime number theorem here is because to prove the prime number theorem itself, you require a lot of heavy machinery, which goes on behind the scenes. And so today I'm going to be presenting you with a slightly longer proof, but it doesn't require anything difficult. There's no prerequisites, no heavy machinery going on in the background, and essentially a proof from scratch. That being said, though, if you can think of any other proofs to proving that this converges, I'll be very keen to hear them in the comments. Anyway, to start with our proof, we're going to state and prove a lemma. And that is if we sum all prime numbers p less than or equal to n, if we sum log p over p, where p is a prime number less than or equal to n, this thing here will be less than or equal to 2 natural logarithm of n. So let's prove this. So what we're going to do is start by making an observation. If I have a positive integer n, and I consider n factorial, let's think about the prime factors of this number. So if n was, say, 10, this would be 10 times 9 times 8 times 7 times 6 times 4, 5 times 4 times 3 times 2 times 1. I think I almost missed the number there. Anyway, what we're going to do is think about all the prime factors. Obviously, the prime numbers that divide n factorial, because this is just n times n minus 1 times so on, all the way down to 1, all the prime numbers are going to be less than or equal to n. So I'll put the product here of prime numbers less than or equal to n. And now let's think about a prime number less than or equal to n. So let's use my example of n being 10. So I'm thinking about 10 factorial. And let's look at a prime number less than 10. Let's say 3. And so I ask myself, how many times will 3 appear in this? And I know that the answer is going to be at least 10 divided by 3, or at least the floor function of that. So I know that this number n factorial is definitely divisible by 3 to the power of the floor of 10 over 3. Why is that? Because I know that every third number here is going to be a multiple of 3. So this number will be 3. I'll have a 3 there in this product. I'll have a 6 somewhere here. And then this would be a 9, for example. And of course, it doesn't mean that this is the highest power of 3 that divides it. Because in fact, in this case, we could, if we had 10 factorial, we can actually get 3 to the power of 4 divides 10 factorial, because 9 is 3 squared. So we actually get 2 3's from that. But that doesn't change the fact that this definitely divides n factorial. And a similar argument holds for any other prime number less than or equal to n. So I can say that the product of all prime numbers p less than or equal to n of p to the power of the floor of n over p, this number here is definitely going to divide n factorial, just by considering each of the prime factors, or each of the prime numbers p less than or equal to n. And so I have that this number here divides n factorial. Now, why is this useful? This means I can then say, if you have something dividing something, oh, why has it gone yellow? If you have something dividing something, that obviously means that this number here is less than or equal to this number here. So I have that pi, so the product of the prime numbers less than or equal to n of p to the power of n over the floor of n over p is less than or equal to n factorial. Now, why is this useful? Well, I want to get a logarithm out of this, and logarithms are very nice when I have products, so let me just take the logarithm of both sides. So the logarithm of the right hand side is nice and easy, that's just log of n factorial. Now what about this left hand side? Well, when you take logarithms, basically everything turns into a sum. So this thing here is simply the floor of n over p, or the sum, sorry, of all the prime numbers less than or equal to n, of the floor of n over p multiplied by log p, like so. So we've proved this result here, that the sum of all the prime numbers p less than or equal to n of the floor of n over p times log p is less than or equal to log n factorial. So we're not quite at our result just yet, but let me clear up the whiteboard and we can continue proving this lemma. Okay, so now that we've established this result, we're going to look to our left-hand side of our lemma. So the sum of p being less than or equal to n of log p divided by p, and use this thing here and say, well, this is simply 1 over n times the sum of p being less than or equal to n of n over p times log p. Now this looks very similar to our the thing we just had. So I can say that this is less than or equal to 1 over n times the sum of p being less than or equal to n of the floor of n over p plus 1. So obviously when you take the floor, you're kind of rounding down, but if I round down and then add 1, I know that this number here is going to be bigger than this number here. So in fact, I could put a strict inequality here if I wanted to, but that's fine. I can keep it as a weak one, and I put log p here. And now the rest is just expanding this sum and using the fact that we have up here. So this is going to be less than or equal to, if I look at this thing times this thing, that's going to give me the thing up here. So 1 over n times log of n factorial. And then what I'm left with is 1 over n times the sum of log p, where p is a prime number less than or equal to n. So hopefully it's clear to see that in this summation here, we have at most n terms, because p is a prime number less than or equal to n. So there's at most n numbers, which could be prime. Obviously it won't be n, but p is less than or equal to n. So there's at most n terms here in this summation, all of which are less than or equal to log n. So this thing here is less than or equal to 1 over n times n log n. 1 over n and the n cancel. So this term as a whole is less than or equal to log n. And similarly over here, log of n factorial, remember that's n times n minus 1 and so on, all the way down to 1. So n factorial is definitely going to be less than or equal to log n to the power of n, because there are n terms in that product, all of which are less than or equal to n. And so I can use log rules to bring this n to the front, so it cancels with that. And so this term here is also less than or equal to log n. So all in all, this is less than or equal to 2 times log of n. And that is exactly what we claimed in our lemma. So definitely not the strongest of upper bounds. We can see there's a lot of wiggle room in these two, but that's fine for the purpose of the lemma and for the purpose of the result we're trying to prove. This is all we need, that this is less than or equal to 2 log n. Okay, so now that we've proved our lemma, let's see if we can use it to prove the result. Now, essentially what we want to do is divide both sides by log of n all squared, but we've got to be a bit more sophisticated than that, because of course this thing here is a sum, so if we want to bring the n onto the inside, we can't really replace the n with p, so to speak, so we've got to be quite sophisticated about what we do. So what I'm going to do is start by considering this sum here, the sum over prime numbers p bigger than n, but less than or equal to n squared, of the thing that we're trying to consider, so 1 over p log p. And now what I'm going to do is, well, say that this is the same thing as just having the sum of n being less than p, but p is less than or equal to n squared, of 1 over log p squared times log p over p. And now what do I know about this thing here, 1 over log p squared? Well, because p is bigger than n, then I know that this thing here is going to be at most 1 over log n all squared. Because of course, if I'm taking the reciprocal, if I want to make this as big as possible, I need to take the smallest possible input. So this is going to be less than or equal to 1 over log n all squared multiplied by the sum of n being less than p being less than or equal to n squared of log base p over p. And now we can use our result from up here, just replacing n with n squared, to say that this sum here is definitely going to be less than or equal to 2 times log of n squared. And in fact, we could probably do a bit better, because we're not starting the sum from 1, we're starting the sum from n, but we don't need to do much better for the result that we're trying to do. So this is less than or equal to 1 over log base, I say log base n, log of n squared multiplied by 2 log of n squared. Well, now I can bring this 2 here, so this will become a 4. And now I've got log n divided by log n squared, so this is just going to be 4 over log of n. And so this is a very common trick, using this kind of multiplying the top and bottom by the same thing, and doing our sum, instead of from 1 to n squared, doing it from n to n squared. And so we've proved that if we sum 1 over p log p from n to n squared, we get something that's less than or equal to 4 log n. And essentially we've done that thing of dividing by log of n squared. But now unfortunately I can't just take n to infinity on both sides, because that will just tell me that the tail of the sum we're interested in converges. Or, well, the tail of it tends to 0, which would suggest it converges, but that's not enough. We need to think about this more sophisticatedly. So what we're going to do is think about the sum that we're considering, so 1 over p, sum over p or 1 over p log p, and we're going to split this sum into p going into different values of, or kind of different intervals, where the intervals are of the form n squared. Okay, let's do this on another whiteboard. Okay, so we're at the final stretch now. We want to use this result to see if we can prove that this sum here, the sum over primes of 1 over p log p, converges. And now, as I say, what we're going to do is split this as a kind of double sum. And so this is going to be equal to, what I'm going to do is firstly take out the first prime number, so when p is 2, so 1 over 2 log 2. And then this is going to be the sum from k being bigger than or equal to 0. So k is just any, k is going over all the non-negative integers, of the sum from 2 to the 2 to the k being less than n, being less than p, being less than or equal to 2 to the 2 to the k plus 1, of 1 over p log p. Now why is this, where on earth does this come from? Well, I've just split the prime numbers up into intervals, and if I look at this, when k is 0, I get p being between 2 to the 2 to the 0 and 2 to the 2 to the 1. 2 to the 2 to the 0 is 2 to the 1, which is 2, so this is considering prime numbers bigger than 2, and hence why I've had to just take out the term p equals 2. And if we look at this, if I think about what 2 to the 2 to the k squared is, well, this is just going to be 2 to the 2 to the k, where 2 to the k I multiply by 2, because that's how you bring down indices into brackets. And that is, of course, 2 to the 2 to the k plus 1. And so my interval here is of the form n squared. And so I can use the result from before and say that this is less than or equal to 1 over 2 log 2 plus the sum from k going from 0 to infinity, and this thing here is going to be less than or equal to 4 divided by log of n, but n in this case is 2 to the 2 to the k. But of course, again, I can just use log rules and say, well, bring this 2 to the k out and say that this is just 1 over 2 log 2, plus 4 over log 2 times the sum from k being bigger than or equal to 0 of 1 over 2 to the k. But this is a very famous geometric series. This thing here just equals 2. And so therefore we've shown that this infinite sum here is less than or equal to 1 over 2 log 2 plus 8 over log 2. So in other words, this thing here, this sum, is less than or equal to 17 over 2 log 2. And therefore it definitely converges. I hope you have enjoyed this solution. I think it's quite a nice solution. It doesn't use anything too complicated, but it's not the easiest result to get to either. You do have to think about how you put the puzzle pieces together to arrive at the final solution. So as I said at the start, if you do know any other solutions, do let me know in the comments. But apart from that, I will stop waffling. Thank you for watching. I will catch you in the next one. Have a great day.